4, and it's a Thursday. I would like to talk about term test 1. Term test 1 will happen on June the 1st, and I think June the 1st, if I'm not wrong, I check. June the 1st is next Thursday, 7 o'clock to 9:30 p.m. Face to face. I will notify you the location on Avenue to Learn. There will be 3 questions and the 3 questions will be similar from homework 1, 2, and 3. When I say similar, 75% similar. Okay, so if you can do the homework without the solution, you'll be fine. I've posted a homework solution 1, homework solution 2, and I also have posted homework 3 and also the solution. Okay, so it's easier for you to study for the term test. So I will tell you the term test 1, where I will test you up to on today. Okay, right. So from now, I'm still going to continue on centric, unsymmetrical, bending. Okay, so the last lecture we did an example. Okay, so now I'd like to highlight the topic of how to identify the position of the neutral axis. Okay, so as we know, the neutral axis is a stress function. So on unsymmetrical bending, the formula we're going to use is stress X is equal to my over Iyy multiplied by z minus by mz over izz multiplied by y. Okay, so if I were to draw a structure now, okay, I'm going to refer to this figure quite a bit. Okay, so I'm going to sketch the position of the neutral axis. But before I do that, I will declare that this is my y axis, and this is our z, and this is rotation about x. Okay, so the centroid, which is parallel to the z-axis by observation, it is over here. Okay, this is by observation, and then the vertical axis, again by observation, is over here. Okay. So the moment that I remember I mentioned this on the last lecture, this is our moment vector m, and m is from the zz axis, right? And this direction is our theta. Okay, we just quickly recall, and from here, okay, on the neutral axis, so I will be referred to the diagram. So position or the neutral axis is oriented such that stress x will be equal to 0. Okay. So if we were to call this equation 1, okay. So if we put stress x is equal to 0, so 0 is equal to my over Iyy z minus by mz over Izz y. Okay. Then when we rearrange the equation over there, we have my over Iyy multiplied by z, and this is equal to mz over Izzzy. Okay. So as you can see, what we have over here, okay, is I'm going to call this axis over here as y and over here as z. And I think to take note is the y and z axis is fixed to the structure or body or member. Okay. So what I mean by that, if I were to copy this figure over here, hold on. If I were to copy this figure over here, okay, and if I paste it, and then if I were to rotate it at an arbitrary angle, I hope I could do this, okay. What it means, so when I rotate our figure, y and z axis will rotate with the member. You'll get what I mean? Okay, it will rotate with the member. Okay. All right, so y and z axis is not fixed in free space, but it's attached to the member and will rotate with the member or will rotate with the structure. Okay, I want you to bear that in mind, and this is important. So we know that we are going to next let tangent theta will be equal to moment about y axis divided by moment about z axis. And over here, the previous equation is equation 2, and this is equation 3. Okay. And for this case, as I mentioned before, note that theta is measured from the z axis, from clockwise is positive and counterclockwise is negative. Okay, so from here we can see that there are two components, and you all will recall that from last week's example. We have two components. So we have one component over here, right? And then we have another component over here. Okay, so we have two components, and we know the vertical one is equal to m sine theta, and this is our moment about y-axis, and the other one is m cos theta, and this is moment about our z-axis. Okay. So with this in mind, all right, we are going to substitute. Okay, we are going to from equation number 2. I'm going to rearrange the equation, so we will have my over mz, right? My over mz. Then you have izz over iyy, and then this will be equal to y over z. Okay, so this I will call it our equation number 4. So with this, we know that, so we're going to substitute 3 into equation number 4. So we know y over z is equal to tangent theta. So we have tangent theta, right? Izz over iyy, and this is y over z. Okay. Now coming back to our diagram over here, okay, I'm going to draw a thick green line. Yeah, I'm going to sketch a thick green line. And this thick green line they have drawn over here, this is the orientation. This is the orientation of the neutral axis. Okay. Again, it's measured from Z, and clockwise is positive, and I'm going to call this angle pi. Okay, I'm going to call that angle pi. And at a very specific position over here, so I'm going to pick a position over here. Right, at a very specific position over there, we have the distance. We have the distance from here to here to the dot. This is our y. Okay. And then we can have another distance. Let me draw a vertical line first. Right. And we have a distance from here to here. And this is z. So at this particular point, we have a specific distance z and y. Okay. So from here, we can write another equation based on pi. So we know that tangent pi is equal to y over z. Okay. And again, note that pi is measured from the z-axis, and clockwise is positive, anti-clockwise is negative. Okay. So from here, we can get the expression. So I'm going to call this equation 5. Okay. So we're going to substitute, and then I'm going to call this equation 6. So we're going to substitute equation 6 into 5. So we get tangent pi